But there is the what you call the worst prediction in physics, which is
that's another one.
a nice little insight about the complicated nature of dark energy. So the observations, as you described, say that empty space has a tiny energy density that accelerates expansion of the universe. But quantum field theory's prediction for what vacuum energy should be when coupled with gravity is much larger.
Mm-hmm.
So this is what makes for the quote. You have a video on this worst prediction in physics. Can you explain this crisis?
Well, there's a measurement, and you can measure how fast the universe is expanding, and from that you get a measurement of dark energy. However, if you then say, well, suppose the dark energy is due to fields in space. So that's quantum field theory. Hey, I know a lot about quantum field theory.
Mm-hmm.
And so we can take the quantum field theory and we can calculate what the density of energy is due to quantum field theory. And basically what you do is you take within a volume the all of the wavelengths, the longer wavelength, the shorter wavelengths, the shorter and shorter, and you can add them all up. And each wavelength adds a certain amount of energy. And if you add that all up, then you get a number. And that number is the rather embarrassing 10 to the 120 power times, that's a 1 with 120 zeros after it, bigger than the measurement of dark energy.
Yeah.
So you go, yuck, that is not fun at all.
Mm-hmm.
And that is because the equation comes to the highest energy or the smallest wavelength particle that you can imagine to the fourth power, since anything to the fourth power is a big deal. So that's where you get that awful number. Now, if it turns out that there is some new physics that's just about at the energy scale we can measure using our biggest particle accelerators, remember I told you that that was a factor. The maximum energy scale, Planck's scale, is 10 to the 15 times bigger than what we can measure now. So let's say that we don't have to calculate up to the Planck scale because something happens, something changes at the energy that we know right now. Well, then that means we don't have to integrate to Planck scale. We integrate to 10 to the 15th less than the Planck scale. And this thing is to the fourth power. So 10 to the 15th to the fourth power is 60. So now, even if we say, Don, he's brilliant. He's going to find something at the LHC tomorrow. It's going to solve all this problem. Now we've solved it. It's much better. It's only different by 10 to the 60 power, which is still pretty bleeding big. So the short answer is there is very clearly something going on, something wrong, very badly wrong in the quantum field theory. We have to have, maybe there's another field that balances out the energy, that cancels it down. And even that, that's not so outrageous. You could imagine that there's another, like we have matter and antimatter, they balance pretty well. Okay, maybe there's something going on. You could cancel that out. That'd be perfect. Canceling something to zero is easy because, +1 and -1, 0, +2, -2, 0. But we still have dark energy. Dark energy is a little bit. So if it cancels, it doesn't cancel exactly because it left over that little bit of dark energy. So that is its own curiosity. Perfect cancellation, pretty easy. Theorists do that, 8 times before breakfast. Imperfect cancellation, much harder.
Just to elaborate that a little bit, what do you think solving, in quotes, solving dark energy would look like?
Well, what you would do is you would hypothesize that there existed some other field that had the reverse effect of existing quantum fields.
But not to zero.
So, but if you had it to go to zero, sure, maybe there's a field that exists at really high energies that we haven't seen yet. I don't know, but it cancels things out and we're cool.
How would we then demonstrate the existence of that field?
Well, that would depend on the prediction.
How do you even come up with a new field?
Like all theorists do. Well, let's add something to my equation and see what happens. I mean, and that's okay. I mean, I'm being glib about that, but that is precisely what you do. You say, what change? We have this thing that works quite beautifully, except it fails here. What is the addition that we need to make that changes very little in the realm that we measured and yet fixes this hard thing? And so you literally just go, da da da, okay, what do I need? Plus 6 or something. And as long as it makes no changes where it would hurt our measurements and fixes the big thing, then that is at least a candidate theory. Now, that doesn't mean it's right, but it at least gives you an understanding of what the right answer should look like.
Mhm.
And so that's the first step, is what should the real answer look like, or what is a possible real answer? And then once you kind of know that, then other people can look and say, well, let me think about a theory that kind of has the required properties to do what we need it to do. So it's a multi-step process, but the first step is, how do we tame this problem without coming up with really terrible predictions that we've already ruled out?
Mm.
And so that's what you do. And that is literally a sensible, viable, theoretical thing, because you have to explore cool ideas.
I mean, one of the reasons dark energy is super interesting is it kind of gives us a mechanism by which we can talk about the deep future of the universe. I mean, we have observations about the expansion of the universe, but it's also giving us the mechanism of that, right? So we
Sure.
can talk about any weirdness, any good model we have that captures some of the weirdness of dark energy might give us insights about how this thing ends, how the universe,
Sure.
about
Sure.
the deep future of the universe, right?
Absolutely. As it stands right now, if dark energy is real, and who knows, if it's real exactly as we've measured it, then as the universe gets bigger and bigger, dark energy becomes a bigger and bigger component of the
Mhm.
energy balance of the universe, and it takes over and it drives the continued accelerated expansion of the universe. And if dark energy gets lower, for some reason that we don't understand, maybe it changes over time, gets smaller. That could change things. If it gets bigger, it could change things.
That is one of the big open questions, whether it's constant over time or not.
Right. And there has been a recent measurement that suggests that dark energy is getting smaller. However, that is a new measurement, not confirmed, blah, 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 blah. Nobody should believe it. But it's a hint that maybe it's changing, which is kind of cool in itself, because the current bias until recently is that dark energy is constant. Now, I want to be super careful because it's misleading. People say dark energy is constant. Dark energy is a density.
Mhm.
Now, think about that. You have a certain density. Let's start with that.
Mhm.
Then the universe expands.
Yep.
So energy is volume times density. If the universe gets bigger and the density is constant, that means dark energy is increasing. It's not just increasing as a fraction and overwhelming ordinary matter, but ordinary matter, as the universe expands, its density decreases because it's constant, and the volume gets bigger, the density drops. Dark energy, until recently, is thought to be constant density.
So that's what's implied when you say constant. You say constant density, which means it's actually increasing because space is increasing. The size of space is
Right.
increasing.
And
Interesting.
so that's a weirdness. And that then ties into the nature of space. Why does that tie into the nature of space? Well, because if dark energy is a field in space, if you increase the volume, you would think the energy density would drop.
Mhm.
But if space is increasing and space is quantized, and I don't know if it is, then maybe what's happening is space isn't stretching, but like little space particles are appearing as the space, there's like bubbles of space appearing, and each bubble contains a certain amount of dark energy. And so therefore that would give you a sense that dark energy is a property of space rather than a field in space. But that's all very hand-wavy, guessworky stuff.
So if you had bet all your money, is dark energy like a real physical, what does that even mean? Thing that exists versus is this just a renaming of the cosmological constant?
Unfortunately, I think it's both. I mean, well, I mean,
Yeah,
it is. It's describing a reality, but it's also maybe telling us something about space.
literally a property of space.
Yeah, I mean, that's kind of what it looks like. Given that it seems to be constant density, that seems to me. Now, this is not something anybody should believe. Please, nobody believe this. But it seems to me that this is leaning towards the idea that A, it's a property of space. B, space is quantized. C, as space is expanding, little quantum of space are appearing. And D, each one of those quanta has a certain amount of energy associated with it. And that would kind of explain the constant density. Now, please, that's not, nobody accepts that. This is
Yeah.
just nonsense.
But a lot of the stuff that you just said is probably experimentally testable. You can probably construct experiment the
Well,
bubbles of
well, finding out the bubbles of space, but those quanta conceivably are Planck size bubbles.
yeah, the quanta.
Well, they'd be quantum of space. I mean, the idea is, you look at a sand dune and it looks smooth and continuous, but you can see individual grains of sand, right? And so what this is saying is as this dune expands, new grains of sand are appearing, and each one of them is a quantum of space.
So what kind of experiments can we do in the coming decades or centuries to understand dark energy better?
I mean, people have been talking about quantum entanglement of gravity. In standard quantum mechanics, a particle can be in two places at the same time. All right. So now you have two particles. So this particle can be in two places in the same time. This particle be two places at the same time. If you put them near one another, well, if they're close to each other, there's a certain gravitational force. If they're far apart, there's certain. And if one is close and one is far, you have another one. You can calculate the effects of gravity having to do with quantum entangled particles being in two places. And people are talking about doing this and trying to see if in doing such a measurement, they might be able to definitively determine whether gravity is a quantum phenomena or a continuous phenomena.
Mhm.
And that is potentially a measurement that could be done soon-ish because the technologies of inherent in all of this recent work on quantum mechanics is allowing people to be able to make instrumentation that might be precise enough to do this measurement. Now, this will not tell us what quantum gravity is. It will not tell us anything, but it will tell us that gravity is quantized. And just knowing that, well, for one thing, it shuts out a whole realm of continuous gravity, and the theoretical community will then turn its attention, forget this stuff, and think over here. Now, that doesn't tell you that space is quantized, but it tells you that gravity is quantized, if it bears out. So, and if gravity is quantized, then people will start thinking more about space being quantized.
I have to ask because you mentioned dark matter is perhaps even more mysterious than dark energy.
Okay.
Can you build up the intuition why it's more mysterious? What is dark matter?
Oh gosh, what is dark matter? A, I don't know. B, it's terribly fascinating.
Yeah.
All right. So, first thing, and the most important thing, because I'm an experimentalist, by God, the first thing is why do we believe there's dark matter? And the reason is that astronomical measurements do not agree with predictions by Newtonian or relativity theory. Galaxies spin too fast, clusters of galaxies move too quickly, and the distortion of very distant galaxies due to the gravitational field of near galaxies disagrees with the prediction from what we see from the observed matter. So there are three very distinct reasons why we are predicting that something is wrong in our understanding of either the laws of physics or the matter budget of the universe. The easiest one to talk about is the spinning galaxies. Now, this is what I'm saying is not unique to spinning galaxies, just easiest to talk about. So, galaxies are observed to spin more quickly than they should if we add up the gravity we see. By all rights, galaxies spinning that fast should blow themselves apart, and they don't. So, What can be the answer? Well, you have the force required for a star to orbit, to move in a circle, and you have the force due to gravity, and they're connected by an equal sign. And the prediction is wrong. So either the force due to gravity is wrong, the force needed to move in a circle is wrong, or the equal sign is wrong. I mean, this is really simple. One of those things is wrong. So, one possibility is simply that Newton's law of gravity, mass times the mass over r squared times a constant, that's just wrong. Another possibility is Newton's F equals ma that we are taught in introductory physics is wrong. Both of those are eminently possible. Over here, maybe we don't understand gravity, or maybe there's more mass than we can see. So these, I mean, it's nice that you can look at this really simply and come up with a list, cookbook of things we can test. And so we've done that. We've gone and said, what are the possibilities? Well, the most obvious possibility is that there is more mass than we can see. There's black holes, there's hydrogen gas that we can't see, whatever. There's something out there. So that was the first thing. So you go and you look, and there's no hydrogen gas because we can see that with the radio waves. That's not it. In the 90s, we went looking for black holes, rogue planets, things like that. Those exist, but not enough of them. That's not it. And so now we're left with there's some sort of matter that we can't see, or we don't understand gravity, or we don't understand inertia. Now, I personally, if you asked me this, I don't know, 25 years ago, I would have said the most likely answer is that we don't understand inertia or gravity. If 20 years ago, 25 years ago, that's what I would have said. No problem. However, there have been a couple of observations that that have caused me to change my thinking, and I think that dark matter is more likely. One of them is called the bullet cluster. So the bullet cluster, there are two large clusters of galaxies. In these large clusters of galaxies, well, any galaxy consists of a couple of components. There are the galaxies themselves, there is the hydrogen gas that surrounds the galaxies, and maybe there is dark matter. And if dark matter is real or dark matter is not real, you will get different answers if those two galaxies pass through one another. The galaxies themselves should pass through one another, basically not interacting. But the big thing is the gas clouds. So if there's big clouds of gas, as the galaxies pass through one another, the clouds should interact and the gas cloud should stop in the middle and be really, really hot. So then you would see, if there were no dark matter, you would see a cluster of galaxies. A cluster of galaxies is a big gas cloud in the middle. And because the big gas cloud in the middle is much more massive than the galaxies themselves, you would expect to see distortions that we call dark matter distortions in the middle. If, however, dark matter is real, the galaxies pass through one another, the cloud stops. Dark matter doesn't interact with the clouds, so it passes through. In that case, you would expect to see the distortions where the galaxies are. And that's what we see. So that is a strong evidence in my mind. The bullet cluster is strong evidence that dark matter is a real thing. And there is another example, which is much more recent. Dark bullet cluster was a while ago, called the Dragonfly galaxies. There's Dragonfly 2 and Dragonfly 4. These are galaxies that rotate exactly according to Newton's laws. And so the fact that they rotate exactly according to Newton's laws says that whatever's causing galaxies to rotate too fast is not a property of matter. But if you had a galaxy where there was no dark matter, for whatever reason, it got stripped off or something, this is one of those lovely ironies that the existence of a galaxy with no dark matter is very strong evidence that dark matter is real, because you can take the dark matter out. So the DF2 and DF4 also suggest to me that dark matter is real. So now, while it remains possible that we need to modify the laws of inertia or we need to modify the laws of gravity, those are possible still. In my opinion, and now this is Don's opinion, but it's probably the opinion of most of the scientific community, dark matter is likely a real thing. Now, that's great. I've taken you all the way to dark matter. So now you're going to ask me, you're going to say, Don, what is dark matter? I'm going to, I don't know. But I know what it isn't. Okay. I know that it is not black holes. I know that it is not rogue planets. I know that we've done the measurements. We've looked across nearly every mass range for compact objects and ruled them out. So if dark matter is real, it can't be made of those. So then you're left with the idea that dark matter is a particle. And that's what we've thought about. The name for the dark matter particle that we've called for a long time is a WIMP, for a weakly interacting massive particle. And we have spent the last, 30 years looking for them in the various ways. There are 3 ways that we might see dark matter. The direct way, which says that dark matter exists literally everywhere in this room, in our laboratory, and the dark matter is passing through the Earth like a wind, and we put up detectors trying to see those. We have done that, and we've seen nothing.
So we should say we have done that for neutrinos.
We've done that for many different types of dark matter. We just simply put detectors in labs deep underground, and we can see neutrinos in them. It's true, but dark matter would have, especially heavy dark matter, what these WIMPs, they have a different signature, and we've seen no evidence of dark matter interaction in these detectors.
So neutrinos are also weakly interacting and also have mass.
They are,
but not enough mass. So WIMPs are heavy on the M.
Right. Neutrinos are indeed WIMPs of a sort. Now, we have to be careful what we mean by WIMPs. They are weakly interacting massive particles, but we can calculate, and there's just not enough mass in them. It's not it.
Got it.
So we need another form. And we have seen zero evidence of this wind of dark matter through the Earth. Another possibility is you look where you think dark matter might be concentrated at the center of galaxies. And if dark matter exists and there's antimatter dark matter, maybe they annihilate and make photons. And so we look for gamma rays and various other signatures of annihilating dark matter. And there are always constantly announcements of, oh, we saw it, oh, we didn't. Oh, the problem is that way of looking for dark matter is hard because there are other ways of making, for instance, gamma rays like neutron stars and stuff. And you really need to understand the details of galaxies really, really well to believe that. And then the final option is what I do, where we smash particles together at high energy. We try to make dark matter particles. If you make dark matter particles, because they don't interact except via gravity, they escape with your detector. So what you're seeing, what you hope to see, is an event where you collide particles, a dark matter particle escapes and you don't see it, but the recoil you see on the other side because momentum is conserved. So you see a blob of energy on this side, nothing on the other side. Maybe that's dark matter. And that also happens with neutrinos. So you need to understand everything about neutrinos and calculate how many of those you see and then hope you see more. And then that might be dark matter. Again, that hasn't worked. So we've ruled out some dark matter particles. But the problem is the range of space of possible mass, if dark matter is of a particulate form, the range of viable dark matter ranges from something like the mass of an asteroid to far lighter than an electron and everywhere in between. And we've ruled out some little spots in that phase space, but that's a big range.
Is it really possible to miss a particle the size of an asteroid?
The astronomical searches were not sensitive to that level of dark matter, but then you would expect that there would be some of those in the solar system. And if they're what we think, like asteroids or something, then we'd heat them up and we'd eventually see them. But if they're really like truly dark matter, doesn't interact with matter, which means they wouldn't absorb energy from the sun, so they'd be really dark. I don't know, maybe they're out there. But the only way we searched for them was a thing called microlensing. So if a massive object, you have a distant star, and a massive object passes between that star and your eye, that star will momentarily brighten.
Mm-hmm.
And so you just look for these, what they call microlensing events, and you count them. And you see some, and we did see some, black holes pass in front of stars, and we've seen them, but we just haven't seen enough. And for very low mass particles like asteroids, they just wouldn't make enough brightening effect to see. So there's like a minimum sensitivity of brightening. And that about a third the mass of a moon, our moon, is about the sensitivity that we had. So, nobody, I think, really thought that these low mass guys were likely. What they thought was more likely they were just unseen black holes, which I thought,
Mhm.
I think is completely reasonable.
Makes
Then when
sense.
that got ruled out, I thought, okay, modified gravity or inertia. Well, now the bullet cluster and dragonfly seems to have ruled that out. So I'm stuck in my head with dark matter seems to be real, and we don't know what it is.
And it makes up a giant percentage of matter in the
It
universe.
is
What is it?
5 times more prevalent than ordinary matter.
Wow. This is incredible.
It
This is
is
so
incredible, and
fascinating.
that's why it's cool. So if someone out there is, a young person who wants to get into this, understanding dark matter is a big deal. I mean, it's 5 times more prevalent. The problem is as I told you, if the mass is ranging from an asteroid to far lighter than an electron, if you get on an experiment that looks at one little range of mass, maybe you weren't the lucky guy that measured the right place, you know? And that's one of the reasons why, as fascinating as I think it is, I'm not doing dark matter experiments because, if you make an experiment that searches one mass range, it'll be blind to another mass range.
Mhm.
So what you need is many groups doing all sorts of radically different experiments, exploring all sorts of parameter space. And with all that said, until you see it, there still is the possibility that maybe we don't understand gravity or inertia right. You
Mhm.
can't rule that out.
If there is dark matter out there, you're hoping it's actually somehow detectable.
I mean, I don't know what it is. I think it's cool. It's very, very fascinating. That is one thing I really do hope in my lifetime is understood, because I'd like to know the answer to that.
And that's the thing that you can see a discovery of.
You got to get lucky, though. I mean, you got to look in the right place, whatever it is.
Just imagine.
Or you have to come up with that really cool theoretical idea that everybody's overlooked, which is another possibility. And there are people who are really, really religiously hating dark matter, largely because we've looked so hard for so many years, and the experiments in today's world are a million times more sensitive than when I was a starting student, and they
Mhm.
still haven't seen anything. And that's why people really hate dark matter. I mean, some of them because
Yeah.
they think we should have seen it by now, but
Yeah.
I don't know.
I mean, I'm a sucker for direct observation. Not indirect is obviously also really great, but direct. Just imagine pointing your telescope in a certain direction, and because of some artifact of cosmology, being able to directly detect a giant amount of a thing that you could say is dark matter.
You would see it things orbit it,
Yeah,
or it would
yeah,
eclipse things in front of it,
yeah. Like
or
in an obvious way, because some of the stuff you mentioned with DF2 and DF4, those are like brilliant indirect um, deductions that there should be something like dark matter, but some obvious, yeah, blocking, occluding, this kind of thing.
we did that in the 90s with experiments called Macho, Ogle, and some others. They looked for a black hole that you just can't see, black hole you can't see. It's perfect. It's a perfect candidate for dark matter. And if there's enough of them out there, remember, there's 5 times
Hmm.
the number of stars, which means there's a whole lot of freaking black holes out there. We should have seen them, and we didn't.